Hi, I'm Eric. I'm here to tell you about RLlib, scalable RL for TensorFlow, PyTorch, and beyond. So I'm going to start this talk by telling you just a bit about reinforcement learning and then the problem RLlib is solving for RL. This talk is also going to cover just the current RLlib project status and new developments for RLlib 1.0. So why reinforcement learning? Just as background, the main difference between supervised learning and reinforcement learning is that with RL, you can more directly optimize for end objectives. So for example, whereas in supervised learning, you might train a model to make predictions about data. So in this example, for example, the model is taking input images of animals and predicting the class of the animals. In reinforcement learning, you're instead training an agent or a policy to take actions in an environment. So it's making decisions about what to do. For example, it might be deciding what ads to show to users. And the agent's gonna collect feedback from the environment in terms of observations, for example, user telemetry, and rewards, for example, revenue. And over time, the kind of goal is for your agent to learn from its experiences and learn to take better and better actions to optimize some metric. The reinforcement learning itself is a very old field in computer science, but it's only relatively recently that it's actually started working really well for applications. And this is because it's been combined with deep learning. So I think one of the first successes in deep RL is, of course, AlphaGo, you probably know about, where DeepMind's agent achieves superhuman performance in Go by leveraging reinforcement learning. RL has found many other applications since then, including e-trading, online advertising, database query optimization, systems control, circuit layout, and many others besides this. So like supervised learning, reinforcement learning scales with compute. So you see this with recent successes, for example, like the AlphaZero, which depend not only on algorithmic innovations, but also specialized hardware and distributed computing. So what this really means is that the software part for reinforcement is actually quite important. And this is the problem RLlib is trying to solve. It's providing a unified reinforcement library that can scale to many different use cases. So what we found is that different users of RL care about different features because they focus on different aspects. For example, teams of research engineers care about building systems and their applications. Academic researchers want to focus on RL algorithms. And applied scientists and product engineers, on the other hand, really want to focus on the application level. So to draw an analogy with the supervised learning world, their deep learning frameworks provide common ways to express and scale tensor computations. And basically all types of users use these common frameworks for their work. RLlib is serving the same role for reinforcement learning. So it provides common APIs for RL, no matter your use case. So what is RLlib? From a user perspective, there's kind of three main API layers to RLlib. First, there's a high-level APIs that make RL accessible to a variety of applications. So of course, you have your basic benchmark environments, OpenAI Gym. There's also environments with multiple acting agents, multi-agent environments. You might be serving policies to external systems that you're interacting with, or training RL policies on offline data in a batch reinforcement learning. RLlib also has a collection of best-in-class reference algorithms. And finally, for the tinkerer or the RL algorithms researcher, RLlib has primitives for implementing a new distributed reinforcement learning algorithms. So I'm going to first talk about these high-level APIs RLlib has. I'm going to show the importance of these APIs through an example. So here we're looking at an example application, NeuroMMO, which is released by OpenAI as a research environment for reinforcement learning. And this is an extremely challenging application. So NeuroMMO has multiple agents acting in a world. So it's multi-agent. Actually has a dynamic number of agents because these entities are coming and going in the environment as they kind of live and die. And agents see complex structured observations. So they're not just seeing like a fixed size image like in Pong or a small vector. They're actually seeing a dynamically varying list of structured metrics about nearby entities in the environment. This is actually pretty similar to many real-world applications where you don't just see a very small fixed size observation, but you see like telemetry or system metrics and so on. So despite this complexity, a neural MMO can basically train out of the box on RLlib. And this is because RLlib APIs are general enough to cover these classes of applications. So I think this is pretty neat because this is something no other RL library can really do. So why is having a unified API important? So beyond the obvious logistical reasons, or you want to switch RL libraries every time you want to do something different, I think there's two really good reasons. First is easy scalability. So any application that runs on RLlib can easily scale with Ray. So in fact, the authors of NeuroMMO found that after integrating with RLlib, they were able to run experiments like just much more easily at higher scale, which really quickly led to new state-of-the-art performance. Second, a unified API enables easy experimentation for applied use cases. This is because when you're working with an applied problem, you're really experimenting with many different ways to express the problem in reinforcement learning terms. So you want the flexibility to try different approaches. For example, a multi-agent approaches, different types of policies and models and so on, which RLlib allows. The second thing RLlib provides is, of course, reference algorithms. So here's a list of all of RLlib's algorithms from our documentation. So you could check this out yourself at rllib.io. You can click in to the algorithms to see more information about how to use them and reference results and so on. So RLlib provides a cohesive API across 14 TensorFlow algorithms and 18 PyTorch algorithms. Allows you to easily scale these algorithms from a laptop to a cluster, and also to customize these algorithms to complex use cases. And these algorithms come from a variety of community contributors to give credit. So obviously the RLlib and Anyscale have added a number of algorithms, but there's also several other companies and university groups that have contributed as well. Finally, if you're an algorithms researcher or you really need to deeply customize an algorithm, RLlib provides primitives for building completely novel algorithms that still seamlessly fit in with RLlib's unified API. As you can imagine, building RL algorithms is a complex topic. So here I'm just going to talk specifically about one aspect of this, which is how RLlib scales algorithms to a cluster. And the example I'm going to use for this is scaling the basic policy gradients algorithm. So if you're not familiar with this algorithm, not to worry. We're not going to talk about the math here, just the computation pattern, which is pretty simple. It's actually just shown on this screen. So the basic steps for running parallel policy gradients is given some current policy, which determines how the agent is going to act. We're going to generate rollouts from the environment in parallel. So basically, we're gathering experiences for this agent. The second step is we combine these experiences together into a data set. And then we're going to update the policy with stochastic gradient descent to improve its estimated performance on those past experiences. So once we have our improved policy, we can broadcast this to the new workers and report metrics and so on. And then keep repeating this until we're happy with the performance of our policy. So in RLlib, to scale this to a cluster, you first have to write this algorithm data flow using a domain-specific language RLlib provides, which I'll show in the next slide. And then RLlib is able to automatically schedule and execute this distributed algorithm with Ray. Yeah, so to make this concrete, this is what the DSL RLlib provides looks like. This is actually basically copy-pasted from RLlib. So you can see we create this rollout step with parallel rollouts over our workers. And then the next step is we take those rollouts and we combine them into batches with the min batch size equal to this configurable train batch size. And then we perform one step of SGD and then update the workers. And this is basically the entire workflow. The final step was we return a metrics wrapper for reporting metrics back to RLlib. So this distributed execution DSL is a new feature of RLlib 085, which makes it much easier to write new distributed algorithms. We've actually ported all our internal algorithms to this new paradigm. It's a big simplification. For example, for Apex and Impala, which are two of the more complex distributed algorithms in RLlib, we've gone from about 400 to 500 lines for defining the distributed part of these algorithms to just 100 to 200 lines. When you consider that this is actually production code and it includes a lot of like extraneous stuff like logging, metrics, and debugging code, this is actually a pretty considerable simplification. I also want to give an update on the community. So we now have an RLlib Slack channel. It's part of the Ray Slack. It has a lot of users, and you can find the link to join at rlib.io. We've seen a steady growth in user engagement on GitHub. So we actually get a lot of ideas and feedback from users, many novel use cases for RLlib on GitHub. And here I'm showing the GitHub issues relevant to RLlib specifically over time, starting from 2017 when the project was founded to the present day. So as you can see, there's kind of been a steady growth, and especially recently there's a increase in speed. So industry-wise, RLlib is part of several industry RL platforms today, and it's also used by many other organizations besides. So some platforms RLlib is part of is Amazon SageMaker, Azure ML, Bonsai, and also SkyMind, among others. So what's next for RLlib? So we like to kind of plan our roadmap based on user feedback. So here are some of the top issues raised by users. So first, there's a lot of community interest in frameworks like PyTorch and JAX. Another thing we hear from users is they want to leverage model-based reinforcement learning. For example, they have problems where the simulators are like extremely expensive to evaluate. For example, they're expensive, or they actually interact with real-world systems. So kind of the extreme sample efficiency that learning a model of the world gives you is really needed for these use cases. We're seeing users run into kind of limitations in our multi-agent APIs, experiment with more novel approaches for multi-agent problems. And finally, we're seeing users trying to leverage more complex models or policies. So for example, transformer networks to do attention over time, and also to handle complex observations within a single step. So in response to the first item of feedback, I'm happy to say that RLlib PyTorch support is now at 100% parity with TensorFlow support. We actually now even have more PyTorch algorithms than TensorFlow, which is interesting. For model-based RL, we're in the process of adding some of the state-of-the-art model-based algorithms to start, including model-based meta policy optimization and Dreamer. To address the multi-agent and complex policy use cases, we're adding two new APIs. First is the distributed execution DSL I talked about earlier. We're also adding a trajectory view API, which will really enable high-performance models that not only look at the present state, but also look over the recent past to attend over time. So in summary, RLlib is the scalable unified RL library. There are a number of new capabilities that have been recently added and are coming for Ray 1.0, so watch out for announcements there. If you're interested in using RLlib or getting involved, you can check out the documentation or find us on Slack at rlib.io. And the RLlib code is also part of the Ray repository on GitHub. Yeah, thank you.